Natural languages are surprisingly restrictive, and yet incredibly generative. From finite resources, we can produce infinitely many sentences. But that raises a question. How generative are they? How powerful is human language compared to the space of all possible languages? Not just natural ones, but artificial ones too, like programming languages or formal systems. And to answer that question, we need a more formal lens. And that brings us to the Chomsky hierarchy. What's language formally? We have alphabets, these are building blocks, and these are sets of symbols. It can contain anything. For example, a binary number system will have 0 and 1. Sigma star is the set of all possible strings that can be generated from the alphabet sigma. But not all of those will be part of a language. A language is a subset of sigma star, but there are rules that tell us which strings are part of the language. Those rules are called the grammar. A grammar is formally defined as a quadruple. It has alphabet as terminals, non-terminals, production rules, and a start symbol. Look at this grammar. The language it generates is a set that contains A, AB, AAA, and it goes on. The Chomsky hierarchy is how we classify grammar by their power. Starting with the simplest, most restricted form at type 3, it goes up to the most powerful unrestricted at type 0. A more powerful grammar can also generate all the languages below it. So a type 2 grammar can produce regular languages along with context-free languages. So here is how it goes for Chomsky type 3. We have a machine. It has states and transition states that take us from one state to another. One of the states is the start state, and one or more states that are accept states. The machine reads strings, and if the string ends in an accept state, it's a word of the language. This machine is called a finite state automata. And any language that is recognized by the automata is called a regular language. The grammar that generates the language is regular grammar. For example, a language that generates even numbers will always have 0 as their last digit in their binary form. And it's a regular language. So this is how it works. We can write A as an empty string or AB, where A gives off a non-terminal and B can be rewritten. This is how the machine reads the string. But this is not powerful enough. It does not have any memory. What if we wanted to create a language that gives as many ones as zeros? We need a counter. Let's say A gives off a string. That string can contain anything, even A itself. That gives us a new power, recursion, and thus hierarchy. This visually is just an addition of a stack as a memory. It recognizes context-free languages. Grammar, Chomsky type 2. Why context-free? Because there is a context-sensitive version. Context-free grammar cannot check for its neighbors, its environment. Context-sensitive grammar can. It can do everything a CFG can do and also allows conditional rewriting. It's basically a Turing machine with a finite memory. It can now copy, change, and move. But these still have restriction. Memory is limited. What if we could grow memory too and delete strings? Basically a Turing machine. The only rule it has is alpha becomes beta and alpha is non-empty, so it can do everything. This is the most general form that encompasses every grammar. So the big question, where is natural language in all this? We can produce most sentences using context-free grammar, and most models are based on that. Let me make it clear, neither context-free nor context-sensitive grammar are talking about semantic or pragmatic context. Anyway, but we fail at some transformations and generations that need counters like conditionals. That's when we need some context-sensitive grammar. So it's really tough to pinpoint natural language. It's most likely mildly context-sensitive, but formal languages fail to capture all the quirks of natural languages. Chomsky perhaps was not able to figure out everything about where natural language fits. But in trying to do so, he created one of the most beautiful formalisms that is also really useful in computer science, a gift of natural language to programming languages.